All right, in this work example, we're looking at some nuclear physics, and the question reads, a stationary isolated nucleus emits a gamma ray photon of energy 0.51 mega electron volts. State what is meant by a photon. So yeah, that's the Greek letter gamma. That's a gamma ray photon. If you know anything about that, say that's a very high energy particle of light. That's the highest energy, the shortest wavelength, the highest frequency. The key idea with a photon is that it is a discrete packet of energy. Okay, it's a particle, like a particle of light. If you said particle of light, that's pretty much what it is. But to really earn these 2 marks, we want to be sort of very precise in our language. So we say it is a quantum. It's a discrete packet, a quantum of energy of, and you could say light, but let's put the fancy science term for light, electromagnetic radiation. Quantum of energy of electromagnetic radiation. Quantum, again, just means it's quantized, which means there's discrete sort of amounts. Think about like a digital clock. It's always showing an exact number, like 1 second, 2 seconds, 3 seconds. That's discrete, right? But an analog clock, like a clock with a hand, that continuously moves from 1 second to the next, right? So that's continuous, right? And it's not quantized. So that's the difference between like digital and analog. Okay, it's quantized. So if you didn't put exactly that down, maybe you want to get sort of the scientific language, but if you knew like a photon was a particle of light, I would give yourself, the marks for that for our purposes here in astronomy. This question comes from ACE Physics A-level. This is an A-level ACE Physics question, but related to our astronomy, right? Because light, what we're looking at in space. Huh? And we've done some stuff with nuclear physics here as it relates to, primordial nucleosynthesis, and we haven't seen the last of our nuclear physics for sure. All right, we want to calculate the wavelength of that gamma ray photon. So the path to the solution here is to recognize that all they give us is the energy. So we need to do something with that. If we use this energy equals Planck's constant times frequency to solve for the frequency, and then we use the speed of light equals wavelength times frequency. The speed of light is known. We can use this equation to solve for the frequency and plug it in here and then get the wavelength that way. So like we can sort of begin with the end in mind here and go, the wavelength lambda is going to be equal to the speed of light divided by the frequency. That kind of sets up our sort of final calculation. But let's go over here and, we got to convert this into joules. So we need the SI unit of energy. So that's one step. And then we got to, find the frequency and plug it all in. So let's work through that together. 0.51 mega means million. So I can convert that capital letter M to this order of 10 electron volts. 0.51 mega electron volts. Good. An electron volt is equal to 1.6 times 10 to the negative 19 joules. So if we multiply this number, 0.51 million, times 1.6 by 10 to the negative 19, we'll cancel out the units we don't want to be in. We'll get to the units that are sensible, the SI units for energy. So calculator, we'll take calculator here. .51 times 10 to the 6. There's our electron volts multiplied by 1.6 times 10 to the negative 19 equals. We get this number, which I want to, instead of counting all those zeros, I can just toggle it over like that, right? So 8.16. So the energy of that photon is 8.16 times 10 to the negative 14 joules. That's the same thing as 0.51 mega electron volts. These are the calculations we did when we looked at energy evolution of the universe, right? We had an equation E of T equals the energy of a typical photon today, about 0.001 electron volts in the cosmic microwave background divided by the scale factor. So we've seen sort of these conversions before, right? Now we're going to plug that in for E and solve for the frequency here. So the frequency is just going to be E divided by H. Since I've already got E here, let's just divide it by H. Planck's constant is 6.626 by 10 to the negative 34. I think in ACE physics, they round this to 6.63. So that's fine if you do your calculation with like 6.63. All right, I've already got that value in my calculator over here, the numerator. So I'm just going to divide it by Planck's constant. Now, when you divide by something in scientific notation, you must use grouping symbols. All right, so I've got that divided by 6.626 by 10 to the negative 34 equals, you get that number. So it has a really high frequency. Short wavelength light, like gamma photons, have really high frequencies, right? The higher the frequency, the lower the wavelength in order to keep the speed of light constant. That's why we use the letter C for that. It's always the same. So here we've just solved for the frequency, right? The frequency is energy over Planck's constant, and its value is in the calculator here, 1.2315 by 10 to the 20. The units, see how joules cancel here? So the units of Planck's constant are joule seconds. Joules cancel, and I'm in reciprocal seconds, which are the same thing as hertz of frequency. It's like, oh, however many hertz of frequency, it's the same thing as reciprocal seconds. How many waves per second? This is an oscillating electromagnetic field. It oscillates that many times, 1.23 by 10 to the 20 times per second. So very high frequency. Now we'll plug that frequency in here with the known speed of light. Now for the speed of light, you may have it in your notebook as the very precisely known value, 299,792,458 meters per second. But I'm just going to go ahead and use the approximate value, 3 by 10 to the 8. It's about 300 million. It's exactly 299 million and change, right? Like I said. And so we'll divide the speed of light by this calculated frequency here. And that will give us, and then again, reciprocal seconds are the same thing as hertz. And so that's going to cancel out those. I'm in meters, which is what I want to be in, right? So that kind of shows that we're on the right track with it too. All right, speed of light, 3 by 10 to the 8 divided by open parentheses, right? Divided by scientific notation, 1.2315 by 10 to the 20. And you get our first answer, that 2.4 times 10 to the negative 12 meters. That's a 2 trillionths of a meter, right? 10 to the negative 12 is a trillion. Imagine taking one of those meter sticks that I've got in my lab and cutting it up into a trillion equal sections, how tiny each one of those sections would be. And that's the wavelength of this gamma photon, 2.4 of them. So it's a really, really tiny wavelength, very high energy particle of light. All right, that's the first one. If anybody needs that up there for a moment or two longer, just go ahead and pause the video, rewind it a little bit, and replay it for yourself at your leisure. If you're live in class right now, think about how lucky you are, right? There's people that are watching this YouTube video hundreds of years in the future going, oh, there was people that was actually in Dr. Schleich's class, like getting that fun quiz Friday. Man, I wish I was there, not living centuries in the future, watching it on YouTube. Maybe, I don't know as I record this what the future will hold. I just can't expect that. Yes, there's a question. I don't know. I would take them all away. The order of magnitude is what's important here. 2.4 an odd factor out front, but it's really, really tiny, right? So if you miss the answer by several orders of magnitude, it might be like you didn't convert the mega correctly up here. So just kind of give yourself the feedback and say, like, where did you go wrong, and try to make the correction. It's up to you, sort of in class right now. How harsh do you want to be on yourself in awarding these marks or taking them away? Kind of thing. We'll talk about that towards the end. All right, now we got to get the momentum. We probably needed some of those answers for that. Let me cue them back up real quick. Let's see, for the momentum, if you guys look on the chalkboard, we've got lambda equals h over p momentum. So really just the wavelength is what we need. So we just kind of want that final answer. Now that's not the answer to momentum, right? That was our wavelength. I already scrolled it down. So remember that 2.4 by 10 to the negative 12. You guys got it written down. Good. All right, so now we're going to solve for the momentum of that. And so we've got the wavelength equal to Planck's constant divided by momentum. It's called the de Broglie relation. This is my favorite equation in all of physics, guys. My favorite one. If we multiply both sides by momentum and divide both sides by wavelength, we'll get rid of those. And we've got that the momentum P is equal to Planck's constant divided by wavelength. Planck's constant is still 6.626 by 10 to the negative 34 joule seconds. That's why it's a constant, doesn't change. And then the wavelength, if my memory serves me correctly, which it does, is this. So more button pushing in the calculator. It's easy to make mistakes on the calculations, you guys. That's why it's good to practice them when we do them in class throughout the week, because it builds your confidence that you're doing it correctly. 6.626 by 10 negative 34 divided by these grouping symbols, 2.4 by 10 to the negative 12, and that's this number. So this photon had basically 0, but it's not quite 0. It's actually 2.8 by 10 to the negative 22 Newton seconds of momentum. Okay, so it's not 0, but it's so low it might as well be. Remember, we're just talking about a single particle of light. So it's kind of a reasonable answer considering what we're talking about. All right, so you got 2 marks for that. Or, you know, you've written down the calculation as I've just presented it, and you say to yourself, well, you know, I'll give myself 1 out of 2 for that. At least I got the correction. Or maybe half out of 2, or, you know, some fraction therein. What do you think is fair? You know, I'm a reasonable person. I'll probably agree with you. Maybe. We'll see. All right, and the paper goes on to read, for this nucleus, determine the change in mass delta M during the decay that gives rise to the energy of the gamma ray photon. Here's where you get to use the famous E equals mc squared, where that is the delta M, the change in mass. So since we know the energy was 8.16 by 10 to the negative 14 joules, all right, remember that we converted the electron volts into joules, and I think it was that number. We're going to divide that by c squared. So if c is 3 by 10 to the 8 meters per second, then you might as well commit this to memory. C squared is just going to be, what's 3 squared? 9. What's 10 to the 8 squared? 10 to the 16. So that's c squared. You just square everything, including the units, right? The units get squared too. So here we've got, I'm just dividing each side of this by c squared, right? So the change in mass is just going to be E over c squared. So that's the energy we already calculated. This is the value of the speed of light squared. And the units, you know, if we sort of expanded the base units here of joules, they're kilogram meter squared per second squared, and the meter squared per second squared would cancel. We'd just be in kilograms of mass. If you type that in the calculator correctly, you can show that the mass is 9.1 by 10 to the negative 31 kilograms. And if you have a really good memory, you may recall, or really good notes in front of you, you might know that, hey, that's the same as the mass of a electron. Very good. That's the mass of an electron. Explain why after the decay, the nucleus is no longer stationary. We talked about how in rocket science, a rocket sitting on a launch pad has 0 momentum. And yet we know the rocket will lift off and start developing momentum. We said, well, how can we sort of explain that? You know, it's like some of the rocket makes it into outer space. That's my best like rocket, you know, blast off noise, because it leaves a lot of the rocket sort of behind as exhaust gases, right? And so we generate thrust by leaving most of the rocket behind. Remember what Tars said in Interstellar, you guys, the only way human beings have figured out how to get anywhere is by leaving something else behind. So this part of the rocket has momentum positive that way. The rest of the rocket has equal momentum down, has negative momentum. That's how we add up to 0. Positive P minus P. You know, P minus P is 0. Same thing here. You have a stationary nucleus that emits a gamma ray photon. And that photon has momentum. We calculated it. It's like 10 to the negative 22 Newton seconds of momentum, which means the rest of the nucleus has the negative of that going in the opposite direction. That's how it adds up to 0. Remember what they started the calculation with. They said a stationary nucleus. If it's stationary, that means its velocity is 0. It has no initial momentum. So it's like momentum is conserved. That's the key truth of the universe. Momentum is conserved. The rest of the nucleus has the same magnitude of momentum as the photon. It's just in the opposite direction. It's moving in the opposite direction. So that's why it's no longer stationary, right? It's going with a tiny little velocity, the opposite way the photon was emitted, okay? And if you want to sort of put that in your own words, if that makes sense, you know, go for it. But the key idea is that we have to conserve momentum. Like the momentum P this way of the photon has to equal the negative momentum of the rest of this nucleus going that way. Momentum is mass times velocity. So the rest of the nucleus is still massive, and it's got a tiny little bit of velocity this way now, so it's no longer stationary. Okay, so that's how we can explain that. All right, whatever grade you want me to put in the grade book, this is a 9-mark quiz. So just make it clear, like how many you feel like you deserve out of these 9. If you're like, well, I wrote down all the answers, so give me 8 out of 9 or 7.5 or like whatever you think is fair. Tristan, you have a question? If you didn't have time to finish it, again, just be fair, to kind of say like, well, I don't want to hold it against myself. I feel like I would have maybe been able to figure it out, maybe take like half the points or, whatever you think is fair. If like, no, I got them down, I give myself full marks for that. That's up to you. This has been another work example with Dr. Schleif. We'll see you next time.